And thank you, the organizers, to give me an opportunity to present one of our recent work in this platform. First, share the screen. Just a minute. Hello? Hello?
Yes,
Hello?
Tamal, you are audible.
Can you hear me?
Yes, yes.
Okay, okay, okay. And can you see my screen?
Yes, we can see your screen. You can continue.
Okay, okay. Just a minute. So, hello. The title of my talk is basically Quantum Networks Boosted by Entanglement with a Control System. And I'm from University of Hong Kong, as Anubhav has mentioned. So this work you can find in this archive link and with my collaborators, Shoptorshi and Julio Kiribella. So the plan of the talk is mainly I will try to discuss about the quantum events and the quantum nature of quantum events. And then I will go to another form, that is history of time orderings. Then I will say quantum time ordering of quantum events. And then I'll move to a new framework for quantum control quantum events and what are the advantages of these control quantum events. And then finally, I will conclude. So general quantum events are generally the CPTP map. That basically means the completely positive trace preserving maps. I think more or less every one of you know what is basically mean by completely positive trace preserving maps. And we know that mathematically these CPTP maps can be written in a particular form, that if this CPTP map E acting on rho, it can be written as summation over EK rho EK dagger, where these EK are said to be the Krauss operators and satisfy some relation kind of thing. But since the closed quantum dynamics are unitary, so every CPTP map can have a dilation, which is called Stein-String dilation, where you can think that your system with an environment is acting with some global unitary, and then you trace out the environment, whatever is retained, that is basically the channel action. This is the basic thing. Now, naturally, the question occurs that if I have, so quantum events. So now, if there are multiple quantum events, one is E, one is F, is it possible that with some probability the quantum system will pass through the E event or some probability with F event? Yes, it is possible. You just toss a coin and whenever it is head, you follow the red line. Whenever it is tail, you follow the blue line and then it's done. So this is the classical simulation. Is it possible to do the quantum simulation? Yes, it is again possible. You prepare a quantum state which is in P00 plus 1 minus P11. So it's a subjective ignorance of up and down spin. And you send this kind of a particle from here. And if it is 0, if it is up spin, then the particle will, the quantum system will follow the red path. If it is 1 or spin down, you are done. So this is also quantum simulation of multiple quantum events. But what is interesting, in 1990, these four professors, this Professor Arnov, Professor Anandan, Professor Popescu, and Professor Vedman, they have come up with an interesting idea that quantum events can also happen in quantum manner. Means that which path the system will follow, that is not a subjective ignorance, that is objective or intrinsic ignorance. Means it's not exactly an ignorance, it's basically an interference between these two paths. So why to consider this kind of thing? Yes. So this is the way that how we can consider this thing, that root over of P0 plus root over of 1 minus P1, that's the superposition of up and down. I pass this particle from this control line and send the particle through this channel. any of these channel. If it is up, then it is red. If it is down, then it is blue path. But it is not neither up, neither down. This is actually a superposition. So whatever happened, that is the quantum nature of multiple quantum events. And obviously, it has no classical analog. So this is generally choice. Choice means whether it is red path or blue path, and it is controlled by the quantum particle in this below line. So why to think about this kind of thing? The beauty of control choice configuration was pointed out in 2005 in two things. One is error filtration. Error filtration means quantum error is more or less a common knowledge in these days. And for the purification of entanglement, suppose you have a noisy channel, if you want to filter the noise out, then you can place two channels in a interfering order or control choice configuration, and you can obtain some fruitful results. Professor Gisa, Professor Linden, Professor Mazar, and Professor Popescu, they have done this work. And these issues related to coherent choice of path or coherently controlled choice is revisited again in the recent days, in 2020 by Abbott, in 2017 by Professor Kiribela and Krijasan, and then 2021 by Venvedvelda and Krivela. So these are the main results. Obviously, there are lots of results. I am not citing all of them. I'm just mentioning few of them. So this is a particular way of thinking the multiple quantum events in a quantum nature. Is there any another form of control quantum configuration? Yes, it is possible. So for that, we have to get a brief history of time ordering. If you ask Galileo, he will say that if I say A is an event, A is before B, then everyone should say A is before B. He is very rigid. Now, if there is Albert Einstein, he will say that, okay, there may be two events. We know that this is called the space-like events. If I am in this frame, then B is before A. And if I am in this frame, then A is before B. So if we remove the frame information from Albert Einstein, that he will say that with no frame information, with half probability A is before B, or with half probability B is before A. So this is his viewpoint. But note that this is basically a subjective ignorance. You don't have the frame information, that's why you don't know. That's why you are saying the probabilistic thing. But the interesting thing is that on 2007 and 2009, Professor Lucian Hardy, he has came up with an idea in context of quantum gravity and said that the lack of time order between two quantum events, not a subjective ignorance only. There can be two quantum events whose order of occurrence is not a subjective ignorance. There is actually no time ordering between these two events. Like composing two quantum operations like E and F, we can compose it like first E, then F, or we can compose it like first F, then E. And we can also put a classical system here, which has ignorance on the 0 and 1 basis, whether it is up or down. If it is up, it will follow the red path. If it is down, it will follow the blue path. And then it is also possible that with some probability it is following the red path, and with some probability it is following the blue path. This is a subjective ignorance on two quantum events. But quantum ordering of quantum events, what does this mean? Again, like the previous one, you can put a superposition here, which is neither up, neither down, but they are superposition. So the ordering between E to F or F to E, there is no particular definite ordering, even it is not a subjective ignorance. So this kind of thing generally called the quantum switch. We will use the term quantum switch, or sometimes we will use the term controlled order configuration. And the first explicit example of this quantum switch and their advantage was pointed out by Professor Giulio Kiribela, Professor Dariano, Professor Perinotti, and Verlion. In this paper, these quantum computations without definite causal structure. And thereafter, lot more work has been published in this direction about to to come up with the several advantages of quantum switch in channel discrimination, classical communication, quantum communication, thermodynamics, metrology. There are plenty of examples. And I try to avoid some of the mainly the mathematical calculations, but for sake of completeness, just let me put some of the calculation that the quantum switch operation, you can think in this form. As I have said, that there is a joint Krauss operator. There we have already said that for every channel E and F, they have some Krauss representation. So this is kind of a joint Krauss representation, which is acting on both this system and on this ancillary. So this Kij will take this kind of form. What this Ei and Fj are meaning? This Ei corresponds to the channel E, Krauss operators correspond to the channel E, and Fi are the Krauss operators corresponding to the channel F. So this is the particular form. And we have already introduced the coherent choice configuration or control choice configuration. There you can see the Krauss operator will take particular this kind of a form. So one particular thing is to notice there that in quantum switch, there are two channels, Ei, Fj. Whatever it is, if it is 0 or 1, both the channels are traversed by the system particle. But in the control choice configuration, when it is up, then it will pass through the first, and when it is down, it will pass through the second, means F. And obviously, there are some parameter, this kind of parameter. These are not any Krauss operator. These are only some complex numbers. And this has some experimental realization that I am not going to in detail. If one interested, they can find this paper to get the more detailed thing. These are the experimentally tunable complex parameters. So the standard quantum switch or standard coherent control choice, whatever done till now, what does it say? That if your control is in 0 state, then first the blue channel, then the red channel. And if it is in 1 state, then first red channel, then the blue channel. And the whole thing is applied on the input state. And standard coherently controlled choice, what does this mean? If it is in 0, apply the blue channel. If it is in 1, apply the red channel. And the whole thing apply on the input state. But we pose the question that is this the most general description for control quantum events? No. We answer that you can think like that. So in previously, you see, there is an entanglement between control and order or control and choice. Here, we pose a scenario where there is an entanglement, a genuine kind of entanglement like control, order, and input. Both are simultaneously entangled. And here, control, choice, and input, both are simultaneously entangled. Like when it is control is 0, then first blue channel, then red channel, and the input state is psi. And if the control is in 1, then first red, then blue, and the input state is phi, and similarly for the control choice configuration. The question is how to realize this? The realization is very simple. Till now, whatever examples the people has done, they assume that this control and this target, they are completely separable. And we emphasize with the fact that let's assume that they can have some kind of correlation. So whatever you will get, that mimics this kind of a particular orientation. And similarly for the coherent control choice. So the question is that why to put this kind of correlation in the input target and order controlling qubit or choice controlling qubit? Yes, it definitely has some meaning, and that's the main goal of this talk. So first we have shown that by this configuration, it is, yes.
So you are saying that the control qubit, not qubit, the control and the input are in a sense they are correlated, no?
Correlated, right.
So
right.
the input is a pure state or it can be mixed, like there is some
obviously
entanglement
if they are correlated, then it cannot be pure, right? It should be a mixed one.
Okay. No, you wrote psi and phi, so I thought, okay.
No, psi here, the joint state, TC. T means target, C means control. Okay.
Okay.
sorry. Yeah. So secured classical communication of a bit via complete eraser channel. What is complete eraser channels? Which erase every information of the input state, whatever state you feed in this channel, whatever row, it just throw out this row and put some value, say 0, put some other state, say 0, or say 1, or some sign like that. So these kind of a complete eraser channels, we can use these complete eraser channels in this kind of network setting to communicate a bit securely. Why to think about? Just some recent experience of WhatsApp where there is a major outage that messages cannot be transferred. So this kind of a noise, we can think that instead of this major outage, we can think that with some particular any message you send to your receiver, it is replaced by a set like 00000, or it resets to 11111. So in such a scenario, it may be useful. Also, you remember that at least WhatsApp claim that their communication is secured. So even the WhatsApp who is providing you the service, they cannot know your message between you and the receiver. So that we actually mean by secured communication, and we mimic this kind of a noise as complete eraser channels. So this is the complete eraser channel. Sometimes we call it pin map, which maps any input state to a fixed state site. For this kind of channel, classical capacity is 0, quantum capacity is 0. So most useless channel. You cannot communicate classical information and obviously cannot communicate any quantum information too. So Alice and Bob, they are sharing these two pair of channels. One is E0, one is E1. As I have said, that one is set channel, which set any input to 0, and one is reset channel, which reset any input to 1. And Alice want to communicate a perfect CB to Bob via this configuration. So what are the possibilities they can do? They can take another ancillary system or a controlling system which actually controls the path of them, means control choice configuration, or which can control the ordering between these two channels, that is control order configuration. So just note one thing at this point, what we have said previously. So this is basically the control choice configuration Krauss operator, and this is the control switch or control order configuration Krauss operators. And we can show that these externally tunable parameters we have said, that alpha I and alpha E and alpha F, we can tune this parameter such that these two Krauss operators or these two channel actions are exactly same. So for the next slides of discussing, I am not going to the control choice configuration. I will only say the quantum switch configuration. And remember, the same thing also holds for control choice configuration, just by tuning the parameter in a particular way. Okay, so what they can send, Alice can send row from here and send a 0 here. If it is 0, say it first go through E1 and then E0, so Bob will receive 0. And if it is 1, then it will first E0, then E1, so Bob will receive 1. So there is no problem, but there is a problem. What is the problem? That since Alice is using this blue particle as 0 and 1 to communicate, this particle may have access, another party, Charlie, he's a third party, he has access on this particle, and by noting what is the nature of this blue particle, whether it is 0 or 1, he can interpret what's the message between Alice and Bob. So this kind of configuration is not possible even if we consider the standard switch kind of thing. So what we have noticed, that if these channels are E0 and E1, this particular channel, then the switch channel, remember the switch channel means both the blue and the green particle together. So the switch channel preserve the 00 and 11 subspace. The total two particle subspace here, either it is 00 or 11, this subspace will be preserved. So obviously, if we put phi plus or phi minus here, the state will be intact from the Bob Charlie side, and that we have actually shown. And obviously, as we have already mentioned, the result for switch is also hold, at least for this case, for uh, control choice configuration. So what we have shown that let Alice and the control share an initial 5 plus, and Alice can encode the message in her qubit just by applying identity or sigma j. Means she privately convert the state to 5 plus or 5 minus, then push it through the channel. And since the total channel preserves the 0011 subspace, the state comes here in the same way, 5 plus or 5 minus. And now Bob Charlie, who is the third party, he can make a measurement on his in a sigma x basis and communicate his outcome to Bob. And then finally, Bob can make a measurement sigma x and judge whether the communicated state between him and Charlie is basically 5 plus or 5 minus. And accordingly, he can decode what is the message sent by Alice. But since Charlie is making the first measurement, he doesn't know what is the outcome on Bob's side. He cannot guess whether the state is 5 plus or 5 minus just by making a marginal measurement, because the marginal state for Charlie for both 5 plus and 5 minus is exactly I by 2. But Bob can do it. Why? Because Bob is informed by Charlie about the outcome. So this is the scenario. So with switch configuration as well as the path control configuration, it is possible to take the help of Charlie, basically WhatsApp, and you can communicate through a set reset channel which completely erases your information to your receiver, and the WhatsApp, that is Charlie, cannot even decode the message what he is helping to communicate to Bob. So this basically mimics the secured communication of CBIT via set reset channel. Even this result is more general. We have proved that any classical DIT can be communicated in this kind of a setting with no leakage to the controller if we have D-orthogonal information erasing channels. Obviously, both the results hold for quantum switch as well as quantum control configuration or control choice configuration. Oh, but important point, I have forgot that the if and only if criteria is that they should share a maximally entangled state in CD cross CD. So this proves that in an uncorrelated, even unentangled fashion, even using quantum switch or control choice configuration, you cannot do the task. Okay, there is one criticism regarding these classical regarding this quantum switch kind of configuration of quantum channels, but I am not going to that detail, but one can show that if someone put these channels in a definite order, even do some manipulation even in the initial or later or in the intermediate position, then also this kind of configuration is not possible. Okay, I'm not going to the detail because I have lost very less time. Yeah. So then we have shown that perfect quantum communication is also possible with this set reset kind of channel if we allow the initial correlation. What they can do, Alice can prepare a GHG state among her, the target particle, and the blue particle, that is a control particle. And she keeps the red particle with her and sends the blue and green particle to Bob and the control one. And the interesting thing is that since this SE0E1 or PE0E1 control switch or control choice configuration preserves the 0011 subspace, the identity on Alice's part and the control switch or control path configuration preserves the GHG subspace. So the initial GHG state prepared in the Alice's lab exactly passed to the Bob, Charlie, and Alice. Now Charlie just make a sigma x measurement on his qubit and communicate the result, and depending upon that, Bob can apply some local operation to obtain a 5 plus between him and Alice. So what we show that with using the set research channels, again in quantum switch or control choice configuration, it is possible to make a perfect quantum communication, even sharing entanglement between Alice and Bob. And in one of our earlier paper, and it's in its archive version, not in the published version, it was shown that for every pair of complete eraser channels E0 and F0, and for every state omega, the switch channels, remember the switch means here the standard switch. The standard switch channels is entanglement breaking. If the channels are individual channels are completely eraser channels, then even quantum switch makes it entanglement breaking, doesn't allow to share entanglement. But if you allow the control and the target to share some initial correlation, it is possible to make the perfect entanglement. And we have concluded that again with the orthogonal information erasing channels in a coherent control configuration, maybe of the order, maybe of the choice, it is possible to establish d-dimensional maximally entangled state if and only if sender and control initially shares a d-dimensional maximally entangled state, because every GHG state can be made with the help of a initial maximally entangled state, bipartite maximally entangled state. And then we generalize this protocol in terms of if there are multiple bobs B1, B2, Bn, and you have a single control operation, you can make a 4-partite or n-partite or n+1, n+2 partite GHG state if there are n number of bobs. And Alice will keep one particle with her and send all the other particles to the channel. What happens that the state exactly transferred to the bob's part, then Charlie can make a measurement and they can got a multipartite GHG state. And it has a consequence. I almost run out of time, so I'm just saying it very briefly. There is a task which is called random receiver quantum communication, where Alice has to send a quantum information to any of these Bob 1 or Bob 2 or any Bn, but the receiver's identity is hidden initially. When Alice will communicate the classical bit of transfer the quantum state, then the identity will be disclosed. So there is no way to send these messages to bobs without having any perfect channel. But it is possible if we share this kind of state, this kind of control configuration. She can make, depending upon this alpha 0 plus beta 1, she can make a C0 operation and get this state. She can send this state, and finally making a measurement on this plus minus basis for both Alice and Charlie. The bob will retain with the state not two bobs, even if there are n number of bobs. So basically alpha 0 tensor n plus minus beta 1 tensor n. And now the receiver's identity is hidden till now. And after this part, the receiver's identity is disclosed, say bob 1. So what happened that everyone except bob 1, here there are only 2 bobs. So B2 will make a measurement on his qubit and communicate in a sigma x basis and communicate the result to the desired bob, that is B1. And it can be shown that the state in the bob B1 slab will be alpha 0 plus minus beta 1. And just by applying a sigma z operation and hearing about this result, it is possible to exactly pass the state alpha 0 plus beta 1 to Bob's lab, even using completely eraser channels, and also when the identity of the actual receiver is completely hidden to Alice. But standard switch can also exhibit this kind of phenomena. This was reported is one of our earlier paper in this journal with the name that random receiver quantum communication. But what is the problem there? Sorry. If you want to do this in standard switch, then the channel, what you can use the individual channels that must have perfect classical capacity. If it is standard switch, means unentangled target and control. But if you allow the target and control to be entangled, then you can even do it with zero capacity channel.
Tamal, you have only 2 more minutes. Please.
Okay. Yeah, and I am in my conclusion. Okay.
Okay. Yeah.
So we have actually introduced a new framework, message control entanglement, both for order and choice. It has a stark contrast with unentangled target control framework that was distributed by, that was exhibited with 2 examples. So first one is secured communication of log d bit of classical information via D-complete razor channel, perfect quantum communication, and perfect distribution of n-partite genuine entanglement with almost asymptotically zero control resource. Why? Because there are n possible parties, Bob, and you need only a single controlling line. But there is a difference. I am not going to the difference in detail, that order target entanglement treats the channels as black box, but this path target or this control choice configuration treat the channels as a gray box, because you remember I said that there are some alpha parameters which is need to tune externally. This makes the channel is gray box, like you have some information or some access on the channels individually. And that's all. Thank you. And up to you.
Thank you, Tamal, for the wonderful talk. The session is now open for questions, so we can have a couple of quick questions.
I have one question. So thank you for your talk.
Sure.
What kind of choice parameter one can introduce by using quantum switch? So in my understanding, choice can be achieved by increasing amplitude of the state.
Yeah.
So
right. So that is the thing. That's why I have said that for quantum switch configuration, it treats the channels as just black box. So whenever we are doing the quantum switch, actual quantum switch, you do not need any access to these external parameters. You just blindly send the state to the channels. But if you want to do this quantum choice configuration, what I have said, then you have to need to access these external parameters, or you have to tune these external parameters. What you have pointed out, basically the amplitude, what you have said that the amplitude of the state, instead of that, actually we have to somehow access to the amplitude of the photon, which is not passing through a particular channel. And when you have control choice configuration, you have a photon which is passing through either E1 or E2. You have to control such a way, or you have to control or tune the amplitude such a way that you can have an axis that if it is not going through E or not going to the F, going through F, that information you should have some access.
So this choice parameter you are introducing by using an environment, or?
Yeah, obviously. And obviously you can, obviously using the environment. But the importance is that it is easier to do the experiment with control choice configuration. So that's why, while control choice is not treated the channels exactly like a black box, just like a quantum channel, but in the experimental perspective, it is really important. Because the choice configuration is easy to experimentally realize.
Okay, thank you.
Thank you for your very nice talk. Each time I listen to you, I learn so many things. So I just want to clarify one thing. So the summary of your talk can be that if you use entanglement between or correlation between the target and the control system, then it can be a better resource than a quantum switch. No.
Right. Obviously. Quantum switch, even also with control choice configuration for both.
Okay, yeah. And in certain scenario, you show that this entanglement is necessary and sufficient condition for performing successfully.
Right. Exactly. Even, but there can be some scenario in one of our thermodynamic work we have shown that where entanglement is not necessary. Even with a lesser quantum resource like Discord, you can do a task what standard quantum switch cannot do. And entangling the target and
Okay.
control is no better there.
Okay. Okay, thank you.
Thank you, Tamalda, again for that nice talk. And hope to meet you again in the next conference.
Yeah.